BENSOUND project, we were hoping to model the movement of a toy car on an incline as it collides with a spring. To do that, we had to consider all of the forces acting on the car. As the car moves down the incline, it's acted on by three forces: the force of kinetic friction that's pointing upwards to oppose its motion, its weight force, which moves it downwards, and its normal force, which keeps it up. As the car collides with the spring, though, the forces acting on it change slightly. The weight force and normal force still act as they did when it was moving down, but now the force of kinetic friction points down the incline as to still act against the car's movement. More importantly, though, the spring force pushes the car up the incline. Additionally, we added a damping force to account for the collision not perfectly conserving energy.
As for the construction of this model, it consists of some scrap wood that I had lying around. I joined it at a 45-45-90 triangle. The actual track length is about 27 inches from the starting block to the springs, and the card I used is from a wooden train set. I chose it because it provided a flat surface for the impact with the spring plate. Overall, this model provided a solid setup that garnered reliable and repeatable results.
Okay, so in order to make our Excel model, we needed to find out some constants. We started by figuring out our friction coefficient with a quick free body diagram where gravity pulls down, friction pulls up. I got our acceleration from tracker, and then I solved for our coefficient, which was about 0.183. We also needed our spring constant, and so I balanced a huge cinder block on 4 of the springs. It was the only way I could get it to balance. So obviously it provided 4 kx force going upward. Then I just solved out for its equilibrium position, and I got a really, really, really high spring constant of around 2,000 newtons per meter. So let's look at some of these things. So first of all, on the left here, we have a lot of constants, which we have to reference constantly. And I gave them all named ranges and stuff. Our time equation is obviously just the previous time plus our dt. The force of friction, right? The force of friction is constant. It's always equal to mu times the normal force, right? But it also has to oppose motion. And so here we pull the sine of the previous velocity and we say do the opposite. Now both the spring force, or both our dampening spring force and our regular spring force have this if L5 is less than or equal to 0. And that just checks that the truck has actually collided with the spring. We put the top of the spring to be a y of 0. Obviously our regular spring force is just kx, and in this case x is the position, right? Because if the top of the spring is 0, then any depression is kx. The dampening force is this force that me and John made up because these collisions aren't elastic. So some energy is being lost, and it's just equal to the damp constant times the velocity, also opposing motion. And then obviously our net force, we just add all our forces up. Acceleration, we just divide by that. Notice that if L5 is less than or equal to 0, we're dividing by the mass plus the mass of the block. This is because, for the course of the collision, the truck and the block are effectively one item. And so it's a really minor tweak because the block doesn't weigh very much, but it's just to keep it accurate. And then, velocity and y, those are just the things that we always have. And then here we have our, our graph. The blue is what actually happened and the red is what's predicted. So turned out pretty good. Oh yeah, one thing that I wanted to mention is this dampening constant. It's a made up force, right? It's not a real force. So we found that constant by making all the other forces accurate and then just tweaking that one until it fit. So that's, something to consider. But yeah, that's our model.